Hello and welcome to Module 1 of Math 211. This is Dr. Brian Powers, and I'm going to be going over the main concepts of this module. So we're talking about sampling and descriptive statistics. This is Introduction to Statistics. So this is the very basics before we even get into any like numbers. So, except for the number 1 in Module 1. That's the first number. Okay, let's go. So this is my little picture of what statistics is in a nutshell. First of all, we're interested in looking at populations. A population is really a large group of individuals, much larger than we could look at each individual one by one. And so in order to know something about characteristics of the entire population, we're going to be looking at a small sample from that population. Okay, that's the basic idea at least. So we take a sample, we run some sort of calculation, and we end up with some statistics. And statistics really are very generally any number, anything that you can do with some data and produce some output. You could call that a statistic. Some statistics are really useful and some of them are not that useful, but that's what statistics are. Some statistics are just a single number, some of them are like a pair of numbers or something like that. Then we have the main things that we do with statistics would be estimation and decision making. This is called inference, where we're trying to make some generalization, infer something about the population from the data, from the sample. So estimation is where there's some parameter or characteristic or something of the population that we're trying to estimate. And we use our statistics to help us do that. The other task is decision making. Is the population this or that? Yes or no? Is this a characteristic or is it not? Is it this or is it greater than that? So that's like a decision-making task. Later on, we'll be calling those confidence intervals and hypothesis testing. Those are the kind of the main first examples of estimation and decision-making we'll get into later. So types of statistics, they can kind of be broken down into two types. We have descriptive statistics, which are numbers that are used to summarize and describe the data. So a descriptive statistic, so you have like you do a sample, you get a bunch of numbers, and you want to somehow boil that down to one or two key descriptors. The average, for example, from the sample average, that's a really popular one. There's other descriptive statistics. So these are statistics that are used to describe your sample data. Then there's inferential statistics. These are numbers that are used to infer something about the population. So these are statistics that are used for the purpose of inference, estimation, or decision making. So I guess that this is a key thing to remember, is that when we're looking at a population, we're interested in what are called parameters. These are oftentimes going to be signified by Greek letters. The Greek letter mu signifies the population mean. Sigma signifies the population standard deviation. Sometimes some books use pi to represent a population proportion. What proportion of the population has some characteristic. And then the Greek letter rho, which actually looks like a p, is used for the population correlation. Now we're probably not going to get into correlation in these modules, but that may change in the future. But anyway, these are just these are characteristics of the overall population. And in general, the parameters are unknown to us, right? They're unknown. If they were known, then we would know everything about the population. On the other hand, we take a sample and we calculate statistics. And we have statistics that are some of the popular ones. X bar is what we use to notate the sample mean. The letter S is for the sample standard deviation. P with a little hat over it. It's actually called P hat. That's a sample proportion. And then the letter R for the sample correlation. Now, just a little note, we're collecting data, and a single number is called a datum. That's the singular form. Data is the plural, just so you know. So data is really a collection of information. And oftentimes it's going to be numbers, but we'll get into that. Okay, so the things that we're looking at in the population are called variables. It's a characteristic of interest that each member of the population has. And they're called variables because they vary from person to person or from individual to individual. Because we're not always dealing with population of people. Sometimes it's a population of cereal boxes, or a population of frogs, or a population of all sorts of things. But each individual from the population has a characteristic, and the value of that characteristic could be different from individual to individual. So each one of these is identified as a variable, and usually given a capital letter as its symbol. Categorical variables are used for categorizing. They are not going to be numerical, or if they are numerical, the number has no numerical meaning to it, really. So if we were going to if we were going to like number the people, like social security numbers, for example, they're categorical because even though they're numbers, they're only categorical identifiers. Their number has no numerical meaning, right? It's just a unique identifier. It could just as well be symbols or letters. It wouldn't change the use of the social security number. Okay, numerical variables are measures or counts of some feature of the individual. So these are variables that take on numerical values, and they're meaningful numerical values. Either we're counting something, how many of something this individual has, or we're measuring how much of something this individual has. Qualitative data, they're values of a categorical variable. Quantitative data are values from a numerical variable. So this is just some terminology you want to be familiar with. Qualitative versus quantitative. So qualitative, like we're looking at qualities, categories. Quantitatives, quantities, right? Discrete versus continuous. First of all, it's good to know that qualitative data is always considered to be discrete, but quantitative data may be either discrete or continuous. So what does discrete mean? Discrete means it takes specific countable values, and it's the result of counting procedure. Like if we're looking at how many siblings a person has, that is discrete because they can have 0, 1, 2, 3. Nobody's going to have 1.75327 siblings. If it's a question like that, if it's something that's counted, it's discrete. So for qualitative data, like if someone was choosing favorite color, for example, their favorite color, we're going to give discrete choices. We're not going to usually have it on a continuous scale, unless there was some way we were putting it on a spectrum that we would assign some sort of numerical value to the wavelength or something like that. So continuous data takes any value along an interval. So usually you can measure to some level of precision that's determined, and you could actually measure it more precisely if you so chose. And usually you can tell it's continuous because it takes on decimal values. Income is considered continuous because we're going down to maybe to the dollar, maybe even down to the cents. Other things like the volume, length, the length of time. Usually, if we're measuring it in parts of an hour, like 3.25 hours, but if we're just counting how old somebody is, their age, that would be considered discrete. So it's a question of, are you counting or measuring? Really, that's the good way to determine it. So you've collected some data, some numbers. So how can you display them? So if you have qualitative data, here we have a person's highest degree that they've completed, we can look at a frequency table. So what we do is we take the different values of this variable. Each value gets a different row, and we count how many times we've observed this value in our sample. So 2 individuals from our sample have as high as a high school degree, 7 have as high as a bachelor's, 20 have an MBA, 3 have a master's, 4 have a law degree, and 4 have a PhD out of a sample of 40. The frequency table, the frequency is just that count. Relative frequency is we're taking the frequency and dividing it by the sample size. So we're getting a proportion of the sample. So relative frequency is always going to be a number from 0 to 1, which can be converted to a percentage by just multiplying by 100. Another way to display qualitative data is with a bar chart. This is very, very handy, very well known. Here's the same data, but displayed in a bar chart. Now with a bar chart, this is a frequency bar chart. Each of the different variable values is along the x-axis, and then the frequency count, that's the vertical. With a bar chart, you're always going to have little gaps between your bars, and the ordering of the bars doesn't necessarily matter. You could change the ordering and the data would still mean the same thing. Okay, some things to not do is stay away from 3D bar charts. They look cool, but they actually make it harder to see patterns in the data. Because of the depth, people tend to ascribe more meaning to that. People look at these and they think the larger the object, the more it should count for. And this top part of the bar makes it look like it goes higher than it really is. Plus, it's really hard. It's hard to kind of move across and see how high this bar is because you have to follow the line and go diagonally. The 3D perspective bar chart's even worse, and because they get smaller as they go further away. They're just awful. Don't ever do them. Okay, pie charts. These are, some people like these. Some people really don't. Pie charts can be useful when you're looking at proportions of things. So what proportion of the whole is for each value. The thing is, you could pretty much get the same information from a bar chart that you can from a pie chart, and people are just generally better at reading the heights of bars than they are comparing slices of a pie. So if I was going to ask you, how much bigger is the teal segment than the blue segment, you might look at that and you'd say, I don't know, maybe it's twice as big, maybe it's a little bit less than twice as big. It's kind of hard to see. That's the point. It is hard to see. So because you can't compare a line that's going straight across. Some people really like pie charts, but once you have more than 3 or 4 slices, it becomes not a very useful way of displaying the data. Never go to a 3D pie chart. That's just the worst. So look at what's going on with this. So what I've done is it looks like more than half of the pie have MBAs because the green part is towards us, and so even though it's half the pie, it is because of the perspective, it gets more than half of the oval. Plus, it gets the whole depth. That's all green, and so the green just overpowers the whole thing. This is a great way of deceiving people, but it's not a good way of being honest with your data. And an exploded pie chart, it's just a waste of space. It's just hard to read. Maybe it looks cool, but it just is not. It's not a useful way of communicating. It's only for show, but it really obfuscates the data. So these are some things to never use. Okay, so let's talk a little bit about how we get this data, how we sample. So generally when we do a sample from the population, we want our sample to be reliable. We want it to be representative of the population we're sampling from. We somehow want our sample to have the same sorts of characteristics as the population does, right? There's various ways of accomplishing this, and they have their pros and cons. Usually, the harder the method to do, the better the result is going to be. So there are cheaper methods that end up giving you not as good samples. So that's kind of we're going to go down the line. First off is random sampling. In a random sample, each individual from the population has to have, at least theoretically, the same likelihood of being selected and put into our sample. So it's actually really hard to achieve this in practice because you have to find some way of reaching at least potentially everybody in the population and to choose them with equal likelihood. In practice, it's really hard to do this because some people are just hard to reach. If you're going to be going on phone records, some people don't have their phone numbers listed. If you're going to be doing a mailing, some people aren't going to return the surveys. There's all sorts of problems that make this difficult, but this, in theory, random sampling is the best method. Maybe stratified sampling is pretty good too. In stratified sampling, you have certain kinds of proportions or strata in the population. Say the population is 50% male and 50% female, so we want our sample to also have 50% male and 50% female. We don't want just from random sampling to have too many men or women in our sample because that might make our sample not representative. So there's certain kinds of features of individuals from the population you want to match the proportions of, like income level or occupation or education level, race, I don't know, whatever kind of characteristic you think is important in preserving that kind of proportions. Stratified sampling, you just have kind of quotas for each of these characteristics, and then you make sure that your sample hits those quotas. A cluster sample, you divide the population into clusters, and then you sample. You pick one or more clusters, and you just get everybody from those clusters. So maybe you're dividing up your city into blocks, and what you do is you just pick 3 blocks out of the whole city, and you just hit every single individual person from those 3 blocks. That would be cluster sampling. Systematic sampling is a way where you have some sort of way of putting all the individuals in some sort of order and just taking every 10th or 100th person. In general, we'd say every kth individual from the population. Maybe you're sampling people who go to a grocery store. So you just stand by the door, and every time somebody enters, you just count. Every time you get to 100th person, you ask them a survey question or something like that. So that's systematic sampling. Then there's convenience sampling, which is really just if you just want to get some data and just it's not going to be very representative, but you just kind of go find a group of people who are really easy to reach, and you ask them. So maybe your neighbors, for example, or you go to some sort of shopping area and you find a group of people and you just ask them. The problem with convenience sampling is the individuals from your sample are probably going to be somehow associated with each other in some meaningful way. They're going to be friends, or they're going to have some sort of similar characteristics. Like, they're probably not going to be representative of the whole population with convenience sampling, and so you might get very biased results. So the idea of sampling with or without replacement. With replacement means that an individual who sampled could be sampled again, possibly. So if you were sampling fish, right, you catch fish, you might measure them, and then you drop them back in the water again. When you catch more fish, you may possibly catch the same fish again, right? Without replacement, it means that you would make it impossible to sample the same person twice. Like when we sample people, we can tell if we're talking to the same person again because we can record some sort of unique identifier from that individual. Okay, so now we'll talk about the different kinds of error. So now this is a word you have to be careful of, because the word error in our common, vernacular means you did something wrong. And that isn't necessarily what we mean when we say error with statistics. Here, error is just talking about some difference between what the population parameter and our sample estimate, right? Our estimate based on the sample. So that error, that difference, in value can come from a lot of different ways. Sampling error just occurs naturally because of the randomness of sampling. You can be sure that your sample statistic, like your sample average, for example, is going to be slightly off from the population average. And generally with sampling error, just by taking a larger sample, you can reduce the sampling error. But then there's another kind of error called non-sampling error, which is more systematic problems. Like if I was doing a cluster sample, that can cause non-sampling error because I am just sampling people in a bad way. Other things that increasing the sample size won't fix is if people are dishonest and they lie, or the other thing would be if my measuring device is just faulty. That can be a non-sampling error. Things that aren't just part of the sampling process would be considered non-sampling error. And you can read more about that. With data, we're going to look at these 4 levels of measurement. So if we ever talk about what is the level of measurement of these variables or of this data, this is what we're talking about, level of measurement. Each level it adds one more restriction to what you have in the previous level. So we have nominal, ordinal, interval, and ratio. First of all is nominal. Nominal is categorical data. It's qualitative. Think nominal like names. Different values of the data have no intrinsic meaningful ordering. So left, right, middle. You could do right, left, middle, left. There's no meaningful ordering there. It's just a categorical. Colors, red, blue, green, orange, puce, and violet. You could order them however you want. It's not going to really matter. You can't say that puce is more than blue. That doesn't make sense. Social security numbers even. There's no ordering that really means anything. Even though they're numbers, it's really nominal data. Now, once we have a meaningful ordering, it becomes ordinal data. Ordinal data is possibly numerical, but it may not necessarily be numerical. So if there's an obvious and unambiguous ordering, such as small, medium, large, low income, medium, high income, these are ordinal values because of the ordering. Now there is not a consistent difference between the values. So for example, the difference between a small and a medium might not be the same as the difference between a medium and a large. Or if I was saying how much it hurts when I swallow, I go to the doctor, how much does it hurt when you swallow on a scale of 1 to 10? I might say a 5. Okay, but what's the difference between a 5 and a 6? Is the amount of pain difference between 5 and 6 the same as the difference between a 1 and a 2? Or a 9 and a 10? No, it's just, they're just in order. Some products on Amazon, one of them is rated as 3 stars and another one's 4 stars. Is the difference in quality between a 3-star and a 4-star the same as the difference between a 4-star and a 5-star, or a 1-star and a 2-star? No, it's just an ordering. It doesn't have a consistent scale. There's no scale that's consistent. And once we have a consistent scale, then we've got interval data. And we now have to have numerical. It has to be numbers. So now we can kind of see how much difference there is between this value and that difference has a consistent and meaningful interpretation. All right. So temperature is a good example of interval because from the difference of 1 degree is 1 degree. Like it's a unit of heat, right? Net worth or net wealth, I should say. Someone might have positive or negative net wealth, but like $1 is $1. An increase of net wealth of $1 is the same whether they're going from $50 to $51 or from negative $20 to negative $19. So with interval, you have this consistent scale, but you don't necessarily have a lowest value, no like 0 value that is a starting point. 0 might be a possible value that you could have, but 0 isn't the lowest. There's no lowest value. Like I guess technically, say temperature, for example, technically, 0 degrees Kelvin is the lowest temperature that something can have. But for practical purposes, we don't consider temperature we don't consider that really for most purposes, right? Now, if there is a 0 starting point, now we have ratio data. you have a 0. Usually it's actually the number 0, and then things can't go any lower than that. So age is a good example of ratio data. You can't go less than 0. Distance, you can't have negative distance. Volume, how much something weighs, these would all be ratio because you can't go lower than 0. All right, so now let's go back to just looking at how we deal with quantitative data, how we can display it. So now let's say I've sampled people, I said how many siblings you have. And I have some data, 0, 1, 2, 3, 4, 5, and 6 siblings, people have said. And I've got the frequency. That's how many people have said I have 0, how many people said I have 7. And we already talked about how to calculate relative frequency. It's what proportion of the total sample. But then you can also calculate what's called a cumulative relative frequency. The cumulative relative frequency, it accumulates as you go down the chart. So you can see that to get the cumulative relative frequency, you take the previous row and then you just add the next row's relative frequency. It just keeps adding up, adding up, adding up, adding up. It may be off by a little bit of rounding because I've rounded off to 2 decimal places, but you should always get to a cumulative relative frequency of 1 at the very end. And so that's what a frequency table would look like for quantitative data. Let's look at some other ways of visualizing or displaying quantitative data. A stem and leaf plot is one way where we take our numbers and so here we've collected a bunch of data. The values are read by taking the stem has a meaning and the leaf has a meaning. In this case, the key at the bottom tells you the stem has a meaning of tens. So the 4 in the stem means a 40. So the 4 means the lowest value in our data was a 44. And then we have a 46, 47, 49. We didn't have any 50s, but we had 63, we had 64, 66, and so forth. So that's how you can read a stem and leaf plot. So the reason this is useful, it preserves pretty much all of our data at a glance, but it also shows you, it puts it in order for one thing, and it shows you a little bit of a shape to it. So we can see here, we had mostly in the 60s and 70s, but we did have one little straggler out, 106. And so you can see when you have gaps, when you have a big concentration around a certain area. We'll see this more in these later visualizations for histograms, but a stem and leaf plots, it's a handy way of showing your data, and then you preserve all of the detail. That's another great thing about it. A line graph we're looking at a frequency line graph. Some people, I personally don't really like these that much because to me, when you connect the dots, it makes it seem like there is some meaning to the values in between. But when we're looking at discrete data, like the number of times a teenager is reminded of something, it's either 0 or 1 or 2. It's never 2.5, it's never 3.5 or 3.3. So there's no meaning to the line connecting it other than a visual connection. To me, when I see a line connection, it implies that we have a continuum and things slowly, gradually change along the continuum. And that to me is misleading. Line graphs would be good for when you have a continuous variable along the x-axis. These histograms are very popular and they're very good. So here we can get a sense of shape. Okay, with a histogram, what we do is we create data ranges, and it depends on how many bars we want to make. So in this case, it was decided to make 9 bars, and then the bins were calculated just evenly spaced out, and you just count what the frequency is in our data, how many times a number popped up that is within each of the bins, and we just count it up. And so we can see if the nice thing is we can really see a shape emerge. So you can really see which of the individuals, like where there's some outliers. Outliers are values that are kind of far away from the others. There's actually a technical definition of outlier, but you get the gist of it. So that's a histogram. It's like a bar chart, but notice some differences, right? You don't have gaps between the bars. The x-axis, you have values that the values that the variable can take going in increasing order along the x-axis, and you have frequency on the y-axis. You can always also have a relative frequency histogram, which is fine. It just means that the y-axis is relative frequency instead of frequency. It just changes the values of the ticks. It doesn't really change the shape at all. A frequency polygon is then a way of you take the midpoints at the top of each of the bars and you connect them. It's a way of estimating a distribution shape. It is. I could see the value someplace. I'm just showing you so that you know what it is, but you read more about it if you ever need to use one. A box plot. This is a great way of summarizing data in a picture. So what we got with a box plot is we're showing you're always going to see the lowest and the highest value among our data. So here the lowest value was about 3.1, the highest value was 7.7. Those are going to be marked off with dots. Sometimes these lines with the little looks a little bit like an arm, a robot arm, but we call them whiskers. That might reach all the way out to the minimum and maximum value. The dark bar in the middle of the box is the median. That means half of the data is below that, half of it's above it. In fact, what we're doing is we're splitting the data into quarters. So the first quarter of the data occurs to the left of our box. The highest quarter of our data occurs to the right of the box. And then the box represents the middle 2 quarters of the data. So the dividing lines are called quartiles. And then the whiskers go out to what's called the last non-outlier. So an outlier is going to be calculated based on how wide is our box. Technically, you take the width of our box. That's called the interquartile range. And we go out 1.5 interquartile ranges to the left and to the right. Anything within that is considered not an outlier. And so we take our whisker and we go out and we're kind of hugging the last non-outlier. The whisker doesn't go all the way out to 1.5 quartiles or interquartile ranges. It just goes out to the last non-outlier. And then any data point that is beyond that is represented by a dot or a little mark. Okay, so that's a box plot. So now we've looked at some visualizations of the data. Let's look at some descriptive statistics. The mean, the measures of center. This is just when we want to say where is the middle of my data. That's a very useful single number to tell somebody. The mean is probably the most useful. We're going to spend more time talking about the mean. It is the average, the arithmetic average, where you take all the values, add them all up, and divide by how many there were. So this is the way you've been taking averages since you've been kind of hearing the word average. Its mean is very it's very informed because every value from our data set goes into calculating the average. The drawbacks could be that the mean is going to be very sensitive to extreme values at the top and at the top end and the low end. Also, you need to have ratio or interval data in order to use the mean. The median is the halfway point. So as long as you have ordinal data, you can use the median. The median, as I said, you basically list your values in increasing order, and you go halfway down the list, and that halfway point is your median. So maybe you have an odd number of data. Your median is going to be one of the values. Maybe you have an even number, so you'd have to somehow go halfway between two values. But the median is the halfway point. Half of your data is below, half your data is above. The mode is the most common value. Sometimes the mode's not applicable. With continuous data, it's really not going to be applicable. But for categorical, so for nominal and ordinal, the mode is going to be certainly the only, certainly for nominal data, the mode is the only measure of center that really can be used. But for ratio and interval, you could talk about the mode, perhaps. But if no value occurs more than once, then the mode is really meaningless. Maybe a mode on a histogram could be meaningful. You could say which bar is the highest, but then you're talking about which bin, a little range of values. Which of those is the most common? So mode is most common. The mid-range, it's still taught, and I don't know why. The mid-range is the middle of your range. Okay, what's the range? The range is from the lowest value to the highest value in your data. So you can, what you do is you take the average of the lowest value and the highest value, the minimum and the maximum. The average of those two numbers, it gives you the mid-range. Mid-range is just as sensitive to extreme values. I don't really know what the pros are. Once upon a time, people didn't have computers, and so calculating the mean was time intensive. So the mid-range was a quick center to calculate. But nowadays, there's no real benefit to using the mid-range. When we're looking at center, one feature that is related is the symmetry or the skew of our data. So symmetry is when you have, if you're looking at, say, histogram, and if you see the kind of, if you symmetric, if it looks like you could fold it over and the shape is pretty much the same on the left and the right, it's symmetric. And with symmetric data, you tend to have the mode, the median, and the mean pretty close to each other. If you have a big skew in your data, a skew is where one tail goes off farther than the other one does, then you will tend to have differences between your mean, median, and mode. So what you're going to have is the tail, the long tail, is going to pull the mean the most. It's going to pull the median a little bit less and the mode a little bit less. So in this case, we would expect to see the mode. Well, I think in this case, the mode you can see is between 10 and 20. That might actually be where the median is as well, but the mean is going to be it's going to be affected by those low values. Some measures so looking at where the middle is an important kind of statistic that summarizes it. The second one that's important is spread. So you know where the middle is. Now, how far does your data kind of spread away from that middle? The simplest statistic is the range. We just, we talked about mid-range, which was the middle of your range. Well, the range is the distance from your minimum to your maximum value. So you take your maximum value minus the minimum, that gives you a range. That's one very simple way of measuring the spread. Another simple one is the interquartile range. This is the range from the first quartile to the third quartile. So it's how far is, you broke your data into quarters, and you say, okay, from the 25% mark to the 75% mark, how far is that distance? How far is that spread? Variance is a little more sophisticated measure of spread. It is, and bear with me, it's the average squared deviation from the mean. So what we do is, for every value in our data set, we say, how far is it from the mean? What's the difference? Well, square that difference. Okay, now average all those squared differences. Now, I say average, but technically we're going to divide by n minus 1 instead of n. This keeps our variance from being biased, and there's a technical reason for that, but just try to remember, if you're doing a sample variance, the variance of a sample data, you need to have this n minus 1 in the denominator. If you're doing a population variance, then you would just divide by the sample size, or the population size. So the variance. Now the variance is a little bit more like I said, sophisticated. The variance is actually not interpretable by itself. Because we've squared all of the values, the units have now been squared, and so the units are not meaningful anymore. You can't, if we're looking at the age of parakeets in a certain forest, that's our variable. This parakeet's 3 years old, that one's 7 years old, and so forth. Well, their squared deviations from the mean might be, 9.37. Another one might be 12.229. These aren't going to be in years. That's going to be in squared years, which is not meaningful. So that's why we have this concept of the standard deviation, where we take the variance and we take the square root again. So we've brought the units back down to the same as our variable, and we can now interpret it. So if I say the mean age of parakeets is 3 years old, let's say 3.3 years, and there's a standard deviation of 1.22 years. Okay, so we can interpret that. That has a good meaning. There's some rules of thumb you can use. So the mean plus or minus a standard deviation is going to be most of your data. That's a good rule of thumb. In fact, there's this empirical rule we'll learn a little bit later. If your data has a certain shape to it, you can say that's going to be about 68% of your data is within one standard deviation. And within 2 standard deviations, you'd see about 95%. So standard deviation does tell you it is a good measurement of spread, how far your data spreads from the mean. So the standard deviation can be very roughly thought of as the average distance from the mean. Now, it's not technically that, because there's some more mathematical stuff going on in there, but roughly speaking, it's the average distance from the mean. So variance and standard deviation are always going to be positive numbers. In fact, all of these measures of spread are always positive numbers.